Hello everyone, this is Anand Ranjan, Assistant Professor, School of Computer Application, Bhamu Banarsidas University, Lucknow. Welcome you all in the video lecture series of Digital Electronics. In this video, we will talk about the Karnaugh map, in short, K-map. Hello and welcome you all. My name is Anand Ranjan and I welcome you all in the video lecture series of Digital Electronics. Today we are going to discuss about the very important and very interesting topic of digital electronics, which is Karnaugh map. Okay, so let me first write. In short, this Karnaugh map is also called as K map, and we normally use this K map for the simplification. So that's why one name is also you can very popularly known is as the K map simplification. K-map simplification, where K stand for Karnaugh. The person who actually invented this technique to solve the Boolean expression. Basically, this Karnaugh map is actually the graphical approach for solving the Boolean expression. So let me first write this point. This is a graphical approach of Boolean function, Boolean function simplification. Boolean function simplification. Okay. If we talk about the classification of this Karnaugh, then this can be classified into two groups. And let me write this. There are two types of K-map. Number one is min-term map, in which after simplification we'll get a SOP expression. So we can say this gives gives the simplified simplified SOP expression. Okay. Another category is the max term map. Max term map. Right? And as you know by the name, after the simplification of the K map using this specific max term map, you will get a POS expression. Gives the POS, or better to say, gives the simplified POS expression. Alright, so as you know, this Karnaugh map is used to simplification of Boolean expression, and of course simplification means somehow it will reduce the number of terms in the present in the Boolean expression. And but there is a very interesting fact you should have to know, that after simplification there is not no guarantee of having a unique solution. Okay, so there may be some changes, some alternatives you will get. So you can write this important note point regarding the Karnaugh map is the simplified expression may not be unique, may not be unique. Okay, so some person may get simplify you using the same map will get a different equation, another will get a different equation. There may be a chance of fair chance of this. Another important thing regarding the Karnaugh map which should have to know that what is the literal meaning of simplification is of using this Karnaugh map. The simplification means we actually reduce the number of and or terms, okay, or by which we actually reduce the number of literals present in the Boolean expression. So the simplification term is actually related to, let me write this, simplification means or simplification implies number one, lesser number of terms, which terms, and term or term, and lesser number of literal, okay. And of course the amount of hardware needed to design a digital system is actually directly proportional to the number of terms that means present in the Boolean expression as well as the literals also. So that's why this Karnaugh simplification or K-map simplification become a very important topic, so that we can able to simplify the Boolean expression to get a compact design of digital system. So let us note this important point that the amount of hardware needed to design a digital system is proportional to the number of terms and literals present in the Boolean expression in Boolean expressions of the function. Okay. So somehow with this schema, if we will able to reduce these terms or literals, then of course we will able to reduce the number of basic components or basic hardware in designing the digital systems. Okay, that's why this simplification is has its own importance. Now let us start discussing the fundamental aspect of Karnaugh map with two variable case. Start with two variable k map. two variable k map. So first of all, let me draw one small rectangular box, because as you know we are considering the two variable case, and in digital with two variable case we can able to generate 2 raised to the power 2, that is 4 different input combination. Okay, so let me take two variable as x and y, and if this x and y are written just beside to each other, in that case this x will be treated as the MSB, while this y will be treated as the LSB. LSB, most significant bit and the least significant bit. And of course with this x and y, just I told you, we can able to generate 4 different combinations, and these combinations could be either 0 0, either 0 1 1 0 and 1 1. So to proceed further, in the first min term map, let me write in this way, because x having its two possible values which are either 0 or 1. Similarly y also have two value 0 and 1, and together x and y we will have the value either this 0 0 0 1 1 0 and 1 1. Okay, this is the all possible for all possible combination with x and y two variable. And if we are going to write this map, means 0 and 1, if we represent it by the variable, then this will be written as 0 will be treated as x bar, while 1 will be treated as x. Similarly here the 0 will be treated as y bar and 1 will be treated as y. So we can also write this combination 0 0 in its variable or literal form, which can be written as, this will be written as x bar y bar, this is x bar y bar, sorry, this is x bar y, because I am just written here y bar, this is not y bar, this is y only. So this is x bar y bar. Similarly this is x y bar, and this is x and y. Sometimes in this Karnaugh map, at the corner we also write the decimal equivalent of this input combination. For example, we are having this 0 0 input combination, so the decimal equivalent of this value we will write at the corner. So we'll mention here this is equivalent to 0, this is equivalent to 1, this is equivalent to 2, and this is equivalent to 3. So this is a very important concept which will help us to for further simplification of the Boolean expression. And of course this small two variable Karnaugh map just we have discussed, this is in the case of min term map. Min term. Now let us also discuss the max term map. Okay. So we will discuss the two variable max term map, in which again we will consider two variable x and y, and of course with x and y we will have value either 0 and 1, 0 and 1. Okay, 0 and 1. Now here we are actually concerned about the max term approach. So in max term approach, the first input combination 00 will be written as x plus y. 01 will be written as x plus y bar. 10 will be written as x bar plus y, while this 11 will be written as x bar plus y bar, because maximum representation we have discussed in the earlier lectures, in which the 0 is represented by its non-complement form, while the 1 is represented by the complemented form, and product term is changed by the or operation. Okay, so this is the this is the max term. This is the max term map. Max term map. Max term. All right. Now let us discuss. See, most frequently we use actually the min term approach for solving the Boolean expression. Now let us discuss the three variable case. Three variable k map. Three variable k map. Alright. Now let us take three variable x, y, and z. So for with x, y, and z three variables, we can able to generate the 2 raised to the power 3, that is 8 different combinations. So we required a box which consists of the 8 8 sections. So to do so, let me draw that diagram. So here we can say we have 8 different uh, you know boxes here. So in which on this side I am considering one variable x, and the remaining two variable I am writing at this side, means y, and z I am writing this side. So as the basic says that with x we have two choices, 0 and 1, while the y and z we could have the four different combinations, and these combinations are either 0 0 0 1, 1 1, and 1 0. So intentionally I am writing this 1 1 instead of 1 0 in a sequence, just because we'll discuss this why I actually mentioned this 1 1 first, then 1 0 next, because we will discuss this part in just coming soon. Okay. So first of all, with this all combinations, if you write their decimal equivalent in the corner, that will be helpful for the simplification of the Boolean expression. So in the first box, as you can say, you will consider horizontally and vertically, then the input combinations you will have 0 0 0, and which is equivalent to the decimal 0 12. Similarly, if you approach row and column wise, the next input combination is 0 0 1, which is equivalent to decimal 1. Further, 0 1 1, which is 3, 0 1 0, which is 2, 1 0 0, which is your 4, 1 0 1, which is 5, 1 1 1 means triple one, which is equivalent to 7, and 1 1 0, which is equivalent to 6. Somehow this is very helpful for the simplification point of view, as well as you can also write the 0 and 1 respective sides. Means here this 0 is actually written as x bar, while this 1 is represented as x. Similarly here this 0 0 is represented by y bar z bar, 0 1 is represented by y bar z, 1 1 is represented by y and z, and this 1 0 is represented by y and z bar. Okay, so this is the three variable case. Similarly we can draw the four variable case also. Four variable k map. When we say four variable k map, it means we have four variables either a b c d or x y z, w x y, w x y and z. So in that case, again, as we say know that with four input variables we can able to generate 2 raised to the power 4, that is 16 combinations. And for that, representing all the 16 combination in a graph, we will have to draw one rectangular box in which there are 16 input combinations we can mention. So let me draw that. So this is all right. And now, as we know, we are dealing with the four variable case in which let me take two variable here and this side, and I am considering the w x y z four variables. So I am taking two variable here, which is w x, and the remaining two variable y and z I am writing at this side. Okay, and of course with these two variable four combinations will I'll write here in this manner. Okay, this is 0 0 0 1 1 1 and 1 0. Here again YZ combinations will have four combinations, that will be 0 0 0 1 1 1 and 1 0. Okay, see, just I have told you that we are not following the sequence just because if you consider the adjacent cell of these boxes, then you will find there will be only one digit change with respect to the adjacent cell, and this will have the beautiful property of gray coding, and which will help us to make grouping of these cells for the simplification. That's why this sequence here we are not following in a proper way. We are considering 0 0 0 1 1 1 and 1 0, not we are considering 0 0 0 1 1 0 and 1 1. Okay, so we are following the gray code pattern to further for the simplification of making groups to the adjacent cell. That will be the beauty of this Karnaugh map. So now let me mention the combination this 0 0 with respect to variable. So this could be written as this represents the w bar x bar, this is w bar x, this is w x, and this is w x bar. Similarly, this will be your y bar z bar, this is y bar z, this is y z, and this is y and z bar. And of course, row and column wise, if you look forward, you will have the first, the input combination, which is 0 0 0 0. Okay, so all zeros are in this box, and which we have to write the decimal equivalent at the corner of in this block. So 0 0 0 0, which is equivalent to decimal 0. So let me write there, let me write here, this is 0. Similarly, the second box, which is 0 0 0 1, so this will be equivalent to 1. Similarly, this is 3, this is your 2. And if you follow the same convention to fill the decimal equivalent right in the corner of the cell, you will mention here you will have 4, here you will have 5, here you will have 7, here you will have 6, and if you consider here you will have 8, here you will have 9, here you will have 10, this is 11, this is 12, 13, 14, and 50. Okay, so rhythmically you can also remember how to fill this. If you are mentioning these horizontal as well as vertical on the edges of this map, you can remember it in this way. This is 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. In this way you can also remember the how, positions of this Karnaugh map with their decimal equivalent value. Okay. Okay, let me write this note point also, because we just not follow the C series of all combinations. The reason I am writing as a note point here, note, and this note says um, only only bit one bit differ from adjacent adjacent cell, and corner also become adjacent. This is important. We will discuss the use case. Corner become become corner become adjacent. Corner become adjacent due to this fact. Okay, all right. So let us move forward further, and we also take few very interesting points regarding this before to take some numerical problem to solve the K-map simplification. And these points are number of cell grouping. Okay, means we have a boolean expression and we translate and transform that boolean expression inside the K-map, then the first and foremost important step is to make the group. So how many cells will be grouped, I'll consider as for the simplification. This point is regarding that, and let me write this. The number of cells grouped in K-map is is a is a power of 2. Very interesting. Means whenever you are go to make a group with the adjacent cell, then it will be always in the power of 2, means 2 raised to the power 2, 2 raised to the power 3, and so on. Okay, so now let me check another point, and this says if all cells in a K map are grouped, then the output the output is always always logic 1 in min-term approach. In min-term map and logic 0 and logic 0 in max term math. This is very important point. If you make a group of all the cells in present in the K map, then this will be the this will give you the logic 1 and 0 depending upon which Karnaugh map you are using. Okay, and let us also discuss this point here, that if you make grouping of the adjacent cell, then what will be the effect of reduction, or what will be the means how many number of variables will be eliminated. This is very important table which you should have to know. Okay, and in that case let me take this two column table in which on one side I am writing the number of cell grouped and number of variable number of variables eliminated number of variables eliminated. Okay, so for example, if we make a group of two adjacent cell, and normally this is called as the pair, in that case we actually eliminate one variable. If we make a group of four adjacent cell, this is known as the quad. In that case we eliminate two variables. If we eliminate the 8 adjacent cells, this is known as the octet. In that case we can able to eliminate the 3 variable. If we make adjacent 16 adjacent cell combination, then we will have eliminate 4. And similarly in general, if we able to make a group of 2 raised to the power n adjacent cell, in that case this will eliminate n variable from the boolean expression. Okay, so this is very general and very important consideration you should have to keep in mind, and this will give the explanation why you actually use the Karnaugh map. Okay, so this is now let us take one more important consideration, that priority of grouping is also important. What should be the priority before when we go for the making a group of adjacent cell? So let me write this important point: priority of grouping. Priority of grouping. So first of all, our prime motive is to look forward the biggest group. Okay, biggest means we will, for example, depending upon the number of variables, we will first of all look forward whether we will able to make a group of octet or not. If it is not there, then we will go for the quad grouping. If it is not there, then we will look for pair grouping. And if we not able to make any group of adjacent cell, then we will leftover single term will be reflected the output of the simplification. Okay, which is the single term. Okay, and finally if we have any redundant term, we will remove that. So we will remove the redundant we will remove the redundant group. So what is redundant group? A group where all the cells are also grouped by the adjacent group. Okay, all right. So this is all about the basic concept related to the Karnaugh map, and let us now try to understand this Karnaugh map K-map simplification with the help of one example. Okay. Let me write first the language of the question which you normally have. This will reflect in your examination. It is like, what is the minimized logic expression? Minimized logic expression corresponding to K-map, corresponding to K-map mentioned below. And let me first draw the K-map. Here we are having the four variable K-map is given to us, in which the variables are W, W, X, Y, and Z. And we can write here the combination just we have discussed earlier. Those are 0 0 0 1 1 1 1 0. Similarly here also this is written as 0 0 0 1 1 1 1 0. We can also write in terms of the variables, which will be like this will be written as w bar x bar, w bar x, w x, w x bar. Similarly here y bar v bar, y bar z. This is y z, this is y and z bar. And in the problem, the number of ones is actually filled, already given filled in this case, and these filled positions are given to you like this. This is already filled case, and you are asked to give the solution. Okay, you are asked to give the solution. Okay. Now, just as we follow the convention, then you will see that we are looking forward the big group. If we are able to, make the group of, because in this case we can able to have the octet also, because but as you know we cannot get any 8 cell adjacent group in by giving the present situation. Yes, of course, at the center you can see that you can have a big quad, four adjacent cell group you can make. Okay, so let me encircle this group like this. This is one, because after quad we will look forward the next bigger adjacent cell group, which is quad. Here you can encircle that. And but if you further look forward, then what you will get that the leftover ones will able to make a group with the adjacent cell also. So in that case, if you make a group of this cell with the adjacent cell like this one with this cell with this, and this cell with this, then what happened that after making the pair, four different pairs, the center quad will become the redundant. So this is the this center part term is known as redundant group. Redundant group. So during this simplification, we will not consider this one. Okay. So when we will not consider this one, we will consider only four different pairs. So by considering the four different pairs, we will write our solution like this. Let us start with the first pair. When this pair you will look forward, then row and column wise you will search for the common attributes in that. So row wise, if you look forward, then on both the cells you will have the W bar X, and if you look forward over in the column section, then you will have then you will have this common Y bar. Okay, this column Y bar. Sorry, let me write it here. This is row I, this is W bar X, W bar X, and column wise Y bar. Then the second group, let me take this group. In this group, the row wise, what you will get, column common, this is W bar, and this is Y and B. Similarly, this group, row wise you will have W, and column wise you will have Y bar, V, and the fourth group or pair, row wise you will have W, X, and column wise you will have Y. So this is the simplification of the given problem. Okay, this is how we actually solve the given problem.